Okay, YouTube, in our last two videos, we explored how we solve both exponential and logarithmic equations. In this video, what we're going to do is we're going to focus on exponential and logarithmic models, where we have some function that is either exponential or logarithmic that describes some, say, real-world situation, and then solving for unknowns given certain knowns using those models and our ability to solve equations now. So we're just going to jump right into I guess you could call it an application situation of an exponential growth model. And take a look at what are the things that we're being asked to find on a regular basis. So we say the concentration of alcohol in a person's blood is measurable. So it says here, suppose the risk R, which is going to be given as a percentage here. So we have the risk is what this value of R is here. We could say risk given as a percentage of having an accident while driving a car can be modeled by this right here, where we say X is the variable concentration of alcohol in the blood and K is some constant. So the first thing I want to do is we could say the concentration of alcohol in the blood is our X value, or our Y value is the amount of risk that you pose in terms of number of times out of 100 you'll drive and get into an accident based upon that concentration of alcohol. So let's go ahead and take a look at this first situation here. It says, suppose the concentration of alcohol in the blood is 0.06, which results in a 10% risk, or R equals 10. It says find the constant K. So in this particular case, what we're given is our capital R here. We're also given this information of risk, alcohol in the blood, which is our X variable here. So if we just go plug this into our function, we should be able to solve for this constant K. So looking at this, we have R equals 3e to the kx, where in this case we're saying the risk would be 10 if and only if our x value here is 0.06. So we have 0.06. And I'm going to clean this up a little bit here, but we have 10 equals 3e to the 0.06, and then I'll write k. So if we're going to solve this, this is definitely an exponential equation. The first thing we want to do is isolate the base of that exponential expression. So we're going to divide both sides by 3 here. And this should give us 10 thirds on the left. We don't want to deal with the decimal. We'll just leave it thusly. And we say e to the 0.06k is what is left. So now that we have this base isolated, what we're going to do is we're just going to rewrite this as an exponent. So rewriting this as an exponent, or sorry, not an exponent, but a logarithm here, which is an exponent, but rewriting it as a logarithm, we could see that we would have log base e. So we have log base e. It's the same base that we have over here, and e is turning into 10 thirds. So we say have log base e of 10 thirds, and that would be equal to now this 0.06k, or the thing we took e to the power of to get this 10 thirds in the first place. So the nice thing about this is, first of all, we can rewrite this as ln instead of log base e of 10 thirds. And then the other nice thing about this is we have this in such a form now that we could divide both sides by 0.06, and we would have a value for our constant k. So with our growth model that we see here, we have the ln, oops, I was thinking 10 already, ln of 10 thirds all over 0.06. And so we'll just get our calculators out here, and we'll do this. We say ln of 10 divided by 3 in parentheses, all of that divided by 0.06. And so we get k, and I'm going to go out to 4 decimal places here. Let's go 3 decimal places, 20.066. So we get an approximate value for k, and you'll notice that I'm writing the approximately equal to symbol. So this value of k, I'm going to go write this up over here. We said, we were able to determine that k is approximately 20.066. So now that we have this k, it says using k, what is the risk if the concentration is 0.17? So you'll notice a few things here. In this first case, or the first thing I want to notice is that we're looking for the R value on our model. This is our model right here. And what we've been given is some X value, or blood alcohol concentration. And it also says using K. So what we have here is our model, which has been refined. This 3e to the kx now becomes 3e to the 20.066x. And this is our model in this particular situation that maps the fact that we would have 0.06 is the BAC for a 10% risk. So now using this model, all we're going to do is we're going to say, well, I was given an X value. We're going to go substitute that in for X, and we'll get a risk factor. So we would say 3e to the 20.066, and we're taking that 20.066 times 0.17, that blood alcohol content. So we'll get our calculators out here, and we'll just type this in. We say 3, now our e to the power button behind the ln key here, we're going to say 20.066 times 0.17, or 0.17. So now if we evaluate this, we get 90.0 0.91-ish. And so I'm going to write that here. Say risk is approximately 90.91, and this is a percentage. So if you had a blood alcohol content of 0.17, you would, theoretically 90 out of every 100 times you're behind the wheel, cause an accident while you're driving that car. Okay, so our risk would be that. So working backwards now, here's the interesting thing. It says if your risk of getting into an accident is 100%, what's the concentration of alcohol in the blood? Remember, this is just a model, and so we could say that theoretically, according to the model, you have 100% risk, even though it's not necessarily 100. And the other thing is this: we've been given an R, and what we're asked to find is what is the concentration of alcohol in the blood, which is the X part. So now we get this. We would say 100% plugged in for our R is equal to 3e to the 20.066 times X. So now what makes this a little bit different is we are well equipped to solve for exponential values here. We solved for the K before. We're going to solve for X in the same way. We're going to divide both sides by 3 to get the base by itself. So we now have 100 thirds is equal to e to the 20.066x. And now we're going to rewrite this as a logarithm. So we say log base e, same as our exponential base. It turned into this 100 thirds. So e turns into 100 thirds. So we'll write that as the argument on our log by taking it to the 20.066x power. So now we're just going to divide both sides by 20.066, and what we're going to get is this ln of 100 thirds instead of writing log base e divided by 20.066. This should be our blood alcohol concentration for 100% risk factor. So let's look this up here. We say ln of 100 divided by 3. We're dividing that by 20.066 approximately, and we get about 0.1748. So x is about 0.1748, and that's approximately X. And we could say, well, then this is really a 17.48% blood alcohol content right here, if we write it as a percentage. So the last thing I wanted to do is actually, because I'm from the state of Nebraska, is kind of compare this to the laws. But it says if the law permits anyone that's, with a risk of getting into an accident of 15% or more should not have driving privileges, then the question is, what's the cutoff level for the blood alcohol content that we should get here? So in other words, we're going to set R equal to 15. And we're going to say, well, what would the X have to be for our R to be exactly 15? We're going to, charge and arrest anybody, or arrest and charge anybody with a DUI if they're above that blood alcohol content. So again, our model here is R, our risk, equals 3e to the 20.066x. And what we're going to do is we're going to plug in 15 for our percentage of risk. We don't want to go over that. So we say, again, we're solving this now. We need to isolate the base first, so we'll divide both sides by 3. In this case, I get exactly 5 on the left, so we e to the 20.066x. And I hope you're seeing the pattern here. We're going to rewrite this as a log base e, and it turned into 5. And this would be equal to that exponent here, 20.066x. And then the very last maneuver we're going to make here is divide by 20.066, 20.066. And so in this case, we get x is equal to the ln of 5 over 20.066. Certainly we could find this here. We say x equals the ln of 5 divided by 20.066. And we would say that 0.0802, so approximately 0.0802, so just above 8% blood alcohol content. So I say, what is Nebraska's law, and does this surprise you? Well, when we look at Nebraska's law, I did look this up, and we say the per se blood alcohol content level is basically they can arrest you at that point if you're over 0.08. And this seems to be, I believe, a national thing, but 0.08 is the per se, and in Nebraska, according to this model, I guess it doesn't surprise me here because it's very close to 0.08. And then you see these zero tolerance laws. I've learned that these are for individuals who shouldn't be drinking in the first place or legally cannot drink, like under 21. If they're even 0.02, then of course they're going to be arrested and charged with something. So that's an example of a word problem. In future videos, we're going to look at general growth models and then some logistic growth models. Cheers.